So I have one last example in this list, and then we'll look at some definite integrals and how you can use substitution to do definite integrals. So let's say I have the antiderivative of tan of x with respect to x. So, well, what is the substitution going to be? Well, what are you going to do? Substitute u equal to x? You can do that, by the way. What would happen? This is almost more of a joke than anything. What would happen if I let u equal x? I mean, technically x is an inside function, right? Well, then what would I get? I'd have du is equal to dx, because the derivative of u with respect to x is 1. So my du would just be 1 times dx, which is the same as dx. So then what would happen? Well, I'd change this into a u integral, and I'd have the integral of tan of u du. And that is a perfectly reasonable and a perfectly valid transformation, but it accomplishes absolutely nothing, right? I haven't done a single thing to help make this easier. So don't try that substitution. This is an example of a substitution that did not help. Okay, so there you go. So let's not do that. But here's what we can do. I can write the antiderivative of tan of x with respect to x. Well, how is this even going to be a substitution? If we can't let u equal x, and if you let u equals tan of x, well, that's good. Try it if you want, but you're going to see that's not going to help either. So what we can do is, well, hey, what is tan of x? This is sine of x over cosine of x. And remember that rule of thumb. If you ever see something in the denominator whose derivative is the numerator, or at least is a factor of the numerator, that's a pretty good sign that that might be a good substitution to try. So actually the substitution here, and this is only apparent because we converted tan of x into sine of x over cos of x, but the substitution that you're going to want to try is u equals cosine of x. Then your du will be negative sine of x dx. Now, we have sine of x dx, not negative sine of x dx, but that's no problem. We can move the negative over to the other side, and we get negative du is equal to sine of x dx. Great. This should work out, because that's our du right here, and then that'll be u, so we'll end up with the antiderivative of 1 over u du. Great. We can handle that, right? This is the derivative of natural log of u, right? Take the derivative of natural log and you get 1 over u. So our antiderivative is actually going to just be natural log of u plus c. But you typically won't see that. Typically what you will see, if you look, like for example, if you look this up in a table, because that's where you can get a lot of antiderivatives, by the way, in the inside table of a lot of calculus textbooks, and if you were to look one up, or even if you Googled this one, antiderivative of tan, you'll probably, pardon me, I'm getting ahead of myself. First, let me put the substitution back in. Let's put cosine of x back in, and you're going to get natural log. What's wrong here? Something went wrong. Here it is, du. This was not supposed to be here, right? Sine of x dx is negative du. So this should actually, let's just back up here. Let's go redo this step. Pardon me. It's been a long day in quarantine. What should this have looked like? This should have actually been, I'll just draw an arrow here so we can go on to our next step down here. So what would you get? Let me do this a bit more carefully. Let me write this as 1 over cosine of x, and then I'll put the sine of x. I'll attach it directly to the dx. I was a bit careless when I did this the first time, and that's why my answer was wrong. The 1 over cosine, that's going to turn into 1 over u still, but the sine of x dx, I should have actually put a negative dx. So I'm going to get the antiderivative of 1 over u times negative du. And then that negative is going to actually come right out. So I get negative the integral of 1 over u with respect to u. That's a bit better. That's what we should get. And then now it's the same strategy now, right? We're still finding the antiderivative of 1 over u, which is still going to be natural log of u, but now we have this negative out in front. So you get the natural log of u plus your constant of integration. Then you plug your u equals cosine of x back in, so you get negative natural log of cos of x plus c, and great. Okay, now we've got an answer, and technically this is the answer. But now we're at the point where I was a bit over anxious to get to this point. This is not typically what you will see if you open up a calculus textbook and you look at one of the antiderivative tables. If you look up the antiderivative of tan of x, you won't see this. That doesn't mean it's wrong, but this is not what you'll see. And here's the reason. Remember, multiples outside of a log can be put inside the log as exponents. And so you'd actually write this as the natural log of cosine of x. And let me be really careful with brackets here, to the negative 1 plus c. And cosine of x, let me do some extra work over here. If I have cosine of x to the negative 1, because I don't have much room left on this page and I want to finish it on this page, cosine of x to the power of negative 1, that's the same as 1 over cosine of x, which that's also known as secant of x. So if you look this up in a table, what you probably see is the natural log of secant of x plus your constant of integration. It doesn't mean that this isn't correct. This is also correct. You can be completely satisfied to leave it like that, but this is what you'll typically see, and that's the reason. It's because of this algebra over here. Okay, so that's the 7th example of this type. We've seen quite a few different tricks, and really it just comes down to practice. It's not like I've shown you every possible curveball that could be thrown your way. You're only going to gain mastery of this by gaining experience and practice. So the best thing you do is just to keep on tackling some. There's 2 more examples I want to talk about before the end of this section, and they're both going to be definite integrals, because every single one we've done so far in this section have been indefinite integrals. But now I want to show you how you can use substitution to do definite integrals.